Hello, and welcome to this evening lecture series. So this is Computer Science Distinguished Lecture Series, and we have the great privilege of having Helmut Pottmann here to give a talk today. And Helmut would be talking about a work that spans differential geometry, computation, and architectural design, and I'm sure we'll hear a lot of exciting stuff from him. Just as how I got to know Helmut, I know him since I think 2003 or 4 when I was still a student, and since then I have collaborated with Helmut many times. I had the luxury of doing it. I spent a year at Vienna as a postdoc with Helmut, and then we went for this adventure at KAUST in Saudi Arabia for 4 years. So we have been through many good and bad phases, and it's a pleasure to have the opportunity of welcoming Helmut to UCL for this talk. So Helmut.
Yeah. Thank you very much, Niloy. Thank you. Yeah, good evening. It is a big pleasure and honor for me to speak here at UCL, which is known to be the best graphics group in the country and one of the finest in the world. So I'm really honored of having the possibility to talk here. I'm actually a mathematician, so neither computer scientist nor architect, and so this is a little bit reflected already in my titles. I will talk about computational differential geometry, but in fact I will not tell too much mathematics, a little bit, and I will show how it is related to what one may call fabrication-aware design. So my research interests are in computational differential geometry, in particular discrete differential geometry, and you may ask, why is differential geometry interesting at all? It has been around for hundreds of years, and I think it is pretty obvious because, as the name says, differential geometry has to deal with data that are differentiable, so functions which are differentiable, and if you have a point cloud or a triangle mesh, this is not differentiable at all. So for example, if you take a triangle mesh and the faces have curvature 0, and at the edges and vertices curvature is not defined in the classical sense. Moreover, in real life you always have some noise, and clearly differentiation is very sensitive, so this is not robust to noise at all. And I'm not interested so much in engineering approaches which circumvent this problem, but I'm actually interested in something which is also appealing from a theoretical side. Then I also looked in the recent years on shape spaces, and you will see in some of my presentation today how this enters our applications, mainly through the exploration of designs. So the feasible designs are a kind of shape space from a mathematical perspective, and we would like to explore this space of shapes. Yeah, and then I would look at various applications, and most recently I look into applications in architecture, and I'm happy to see a few of my friends, I would almost say, from architecture here. So, and what we would like to do, we are interested in shape modeling, but considering important aspects of the function and the fabrication of that shape already in the shape creation phase. So the motivation is differential geometry, as already said. The classical theory does not apply. And why is it still interesting? I give a very simple example. This is actually from work with Niloy, so this is why I picked it. This is scan alignment. So we have a bunch of scans from this standard Stanford bunny here, and these are point clouds, and they are not in the same coordinate system, and we would like to merge them into one model, so the same coordinate system. This is a matching problem, and in order to detect correspondences, curvature analysis is very useful. It helps to detect correspondences. And there is one way to do it in this case. You can locally, if you have such a point cloud, numerically you fit some smooth approximation to your point cloud, and you can extract the curvatures there. But you will see during my presentation that this is by far not sufficient for many of the applications we have in mind. And at the beginning, before I go into more detail, I would like to tell you just an example of computational differential geometry, which was somehow invented by several people and groups, and which goes as follows. So we have an object. This is in this case case actually a scan of a fragment. So you told me today about this problem, yeah? A scan of a fragment of some artifact, and it has some rough surface. It is a scan, so at best this is a triangle mesh, and we would like to assess curvatures at various points of that scan. And what we do, we place balls at the location where we want to assess the curvature, and the size of the ball, the radius, determines the neighborhood on which we want to charge it. If I have a big ball, I want to charge it on a larger scale, and if I take a very small ball, I'm willing to even recognize small features, small details. And then we do something very simple. You intersect this ball with this solid. This gives you some intersection objects. And I think it is obvious that the volume of this object must have to do something with curvature. Think if you have something completely flat, and if you center a ball there, you will have exactly half the ball volume, and if it's curved more, you will have less, and so on. And so the volume of intersection must be related to some curvature, and a more detailed analysis shows it is related to what we call mean curvature. I will say a little bit more later on what this mean curvature actually is. So you see here this Taylor expansion of the volume of this intersection with respect to the radius. The first part is the expected part. This is half the ball volume. And then you have a first correction term which comes with the force power of the radius, and here you see this mean curvature sitting, and then you have some higher order terms, and one way to define a mean curvature at this scale is to cut away this term and solve this equation for h, for the mean curvature, and you can define it as a mean curvature on a certain scale, and you would get an assessment of mean curvature like this, and this was successfully used as part of the method. So this does not solve the entire problem, to reassemble fractured objects by geometric matching. So you have a broken artifact and you scan various fragments, and the question is, can the computer reassemble? And here we assume sufficiently thick models so that there is some significance in the fracture surfaces. So for very thin shells it would not work. And in quite some cases we could achieve a reasonably good assembly, and there is a lot more work to be done here. And just a few minutes ago, basically, I learned that Tim Weirich is one of the people who are working on this topic from various perspectives, and of course solving much bigger problems, and not just something like 30 fragments, but maybe thousands of fragments. Now let us go to architecture. That's actually the person who brought me into architecture is sitting here in the first row. This is Robert Esch. So I was invited by him in 2003 to a conference in Baltimore, and this was from the Smart Geometry group, and I was amazed how much these people are interested in geometry, and even more so, I was amazed that you found my talk interesting, which I thought is not that great. And this gave me the idea to look a little bit into architecture as an application. So my application today are these large-scale architectural projects which are around at many places of the world, and many of them are actually designed here in London. And this is what we call freeform geometry, and it is obvious that such freeform geometry is not so easily realized on this large architectural scale. If you have a freeform surface, it is really freeform. You have to break it into panels in order to build it, and every two panels will be different. They may be double curved. You need molds and so on. So this is a challenge. I don't go into details because the specific problems I will outline later. So we can only build approximations, and what I'm interested is not first design something and then realize, oh, it's not so easy to build, and then change it, and then it is manufacturable, but then it doesn't stand, and so on. So integrating everything, if possible, into one system. Now, you will ask, why do we know about the demands in practice? And one way why we know it is that some years back I founded, together with some colleagues, a company called Evolute. This is a very small company, a spin-off from my group, but they do real projects, and I show you a few real ones where they have been involved, so like this Yas Island Marina Hotel in Abu Dhabi, where they did the mesh layout and the supporting beam layout, or the Museum of Islamic Arts in the Louvre, where they worked on this roof structure, which is composed here of flat quadrilaterals and triangles. This is the ready project, or again in Paris, currently under construction, maybe already finished, I'm not quite sure, 3 pavilions on the first platform of the Eiffel Tower, exhibiting some curved glass facades, which was actually done with a lot of geometry that we have developed over the past years. Yeah, here you see something from the construction. So an overview of what I will talk about today. The first thing is planar quad meshes, and this is somehow, in my view, a discrete differential geometry which is motivated by application. Then I will talk a little bit about the shape space, the design of self-supporting surfaces, and then some very recent work, form finding with special meshes done in a simple way, and if there is time, a few pointers to further work. But let me dive directly into the subject. I will often use today the term polyhedral mesh. This is a mesh whose faces are planar. These faces could be quadrilaterals. These are then these planar quad meshes, which are probably, from a theoretical perspective, the most interesting ones. Then there could be mixed species, like here a mesh from flat quads and triangles, or it could be flat hexagons. All such things are polyhedral meshes. And let us say a little bit more on these planar quad meshes. The interesting thing is that these planar quad meshes reflect somehow the curvature behavior of the underlying surface. They are aligned in a special way, and this alignment is along what a geometer would call a discrete conjugate parametrization. So a parametrization of a surface writes each surface point in depending on 2 variables u and v, and if the determinant of the 2 first derivative and the mixed second derivative vanishes, we speak of a conjugate parametrization, and a discrete version of it is exactly these planar quad meshes, and because of the second derivative, obviously this thing is related to curvature, and one knows a lot about such conjugate parametrizations. The computation of such a planar quad mesh can be based on nonlinear optimization, but later today I will show you that we have something new, not to use optimization in the standard way. And the optimization criteria will be, of course, the planarity of faces, and then it will be the aesthetics. So maybe let me point to this. If you have such a mesh, you have some natural flow of some mesh polylines, and you don't want a very zigzag behavior unless it is a design element, but in many cases you may want a really nice flow. So this is what we call here aesthetics, or fairness of mesh polylines, and you may have already a given design and you want to stay close to the given design. So proximity to a reference surface. And the important thing really is not to come up with a numerical optimization that fulfills this criteria. It is to appropriately get a starting guess for the optimization, because this is nonlinear, and this means if you start with a totally weird initial mesh, it just will not converge. And this is a main message today, that from differential geometry or other geometric insight, you get a way how to initialize your algorithms, and this will allow you to succeed. And if you just, once, I remember we got from an architecture company a mesh which we should planarize, a quad mesh. And they did nothing else than in a certain view, they projected a grid, a stupid rectangular grid, onto the surface, and then please, Mr. Potman, with your magic numerical optimizer, please planarize. Of course we could planarize, but either we deviated from the reference surface too much, or we could not achieve the mesh fairness. So this is not going to work. I show you an example where it worked well. This is a project of Zaha Hadid Architects, which got approximated here by a planar quad mesh, and this is a success case. In architecture, this is called rationalization. because you make it possible to be manufactured, to be fabricated. And this is just another rendering of the thing. Of course, you see that it is faceted. It has to be faceted. It is planar quartz. But overall, it may give the appearance of some kind of curved freeform surface. So let me say a few words about discrete differential geometry. So it develops discrete equivalents of notions and methods of classical differential geometry. And so the classical theory later appears as a special case, a limit case actually, as a limit case of the discrete theory. So in some sense, the discrete theory is richer. The classical thing is easier. Yeah? Some basic structures of this discrete differential geometry are related to the theory of integrable systems, and most importantly, these planar quad meshes actually, and there's an entire book on that, just to be mentioned. And what all these people who work in the field will tell you, one has to discretize the theory, the geometry, and not the equations. Because, of course, you could go ahead and look at the differential geometry book, and you have a lot of differential equations, and every numerics guy will tell you how to discretize it. It may lead to a computational scheme for a specific application, but not to the insight we need here. And there are several ways of discretizing, and it is not always clear which one is the best, and sometimes it depends on what you want to do. And there are even special topics which in themselves fill a book. For example, generalized curvatures, there is an entire book on that, and actually this book only deals with triangle meshes. So in this sense, it's very special. So for those who forgot it, I just recall a few things about curvature. If we have a curve in the plane, we have a locally best fitting circle, also called the osculating circle, and the inverse value of its radius is the curvature of the curve at that point. Then if we have a smooth surface, we pick a point, we have a tangent plane, we have a normal to the tangent plane called the surface normal, and we can then pass planes through the surface normal. And we can intersect these planes with the surface. We get planar curves, and for the planar curves, we know how to compute the curvatures. So for each direction here, each plane through the normal, we have a so-called normal curvatures. And if you play this game, you will find that for two orthogonal positions of this plane, we will get the extremal values of these normal curvatures, and they are called the principal curvatures. So in my figure, this is here the XC and the YC plane. These are the principal curvatures, and their product is called the Gaussian curvature, which plays a unique role in differential geometry, and the arithmetic mean is called the mean curvature I was talking about before. And of course, if you have, for example, a plane, everything will be zero, and it's easy to see what happens for other special surfaces. So Gaussian curvature 0 is not only true for the plane, it is true for every surface which you can unfold into the plane, like this piece of paper. Oh, I'm sorry, that's bad, yeah? So everything which you can, say, make from a piece of paper, yeah, is a developable surface. So these are the important surfaces, of course. And so it can be mapped into the plane without distortion. Here's an example. Locally, they are special ruled surfaces. So a ruled surface carries a family of straight lines. In this example, the lines are parallel, but this is not important. What is important, however, to guarantee developability, that along such a straight line, a ruling, we have a single tangent plane. So this tangent plane touches the surface along an entire line. This makes it developable. And a discrete version will be, for example, you take planar quadrilaterals, put them together. Such a strip of planar quadrilaterals is a discrete model of a developable surface. It's trivial, of course, if you have flat faces, you can unfold into the plane without stretching or tearing. And if you can refine it so that this stays planar, these faces stay planar, in the limit you will get a ruled surface, and the limits of these face planes will exactly be these tangent planes that are constant along the rulings. Now, one has at each point of a surface two orthogonal tangent directions to which we have these principal curvatures, so the extremal value of curvature, and one can integrate these directions. Means we look at curves on the surface that always follow this extremal normal curvature, these principal curvatures. And another characterization is if we have such a principal curvature line, and we take the surface normals at the points of this principal curvature line, these surface normals will form a developable surface. So this is another geometric characterization. And by the way, this was used in architecture in this Eiffel Tower project. So these beams, the supporting beams, are along principal curvature lines. The normals are developable, which means the beams can be made from flat material, which is then bent. In fact, it's very interesting that this, not simple, but this application scenario is in some sense like a lecture in differential geometry. There are many things which you can demonstrate at hand of this simple design. So we may ask more questions if we are interested in these planar quad meshes. For example, we may ask, can we make sure that these panels are as close as possible to rectangles? So we will see immediately precise rectangles will not be possible, only for very special shapes. Yeah? But as rectangular as possible. And again, we do not want to set up some optimization with some criterion which makes it as rectangular as possible, and then in some cases we will succeed, in others we will not. We will not get any insight. So we need a discrete counterpart. We see that as rectangular as possible means right angles, yeah, as close as possible. Then we also have these properties that these are conjugate curve networks. Differential geometry will tell you a conjugate curve network, which is also orthogonal, is a network of principal curvature lines. So you immediately see that these objects must be a discrete counterpart of principal curvature lines. And I mentioned two of them which are interesting. One is the so-called circular mesh. A circular mesh is a quadrilateral mesh where each face has a circumcircle. So you see it very clear here. And the other one, which is for architecture even more interesting, is a so-called conical mesh. A conical mesh is a mesh made from planar quads where at each vertex you have generally 4 planes meeting of these faces, and you require that these 4 planes are tangent planes of a rotational cone. 3 planes, of course, are always tangent to a rotational cone, but 4 is special. Like in the plane, 3 straight lines are always tangent to a circle, but 4 straight lines are not. This is a special condition, and so these cones have rotational axes, and these rotational axes quite obviously are a discretization of a surface normal. In this case, a very precise definition of a surface normal. And let us argue a little bit on this simple object, because here it is really easy. If we take an edge, so we have here a cone, and we have here a cone, and we have these 2 face planes, they must be tangent to both cones. This is a definition of a conical mesh. So if you have 2 tangent planes of a right circular cone of a rotational cone, the bisecting plane of these 2 must pass through the cone axis. This is by the symmetry of the cone. Yeah? And therefore, this plane, both axes must lie in the bisecting plane. So these 2 axes are coplanar. And we could continue along such a mesh polyline. So the next axis again would be coplanar, and so on. And we will see immediately the discrete surface normals along a mesh polyline form a discrete developable surface. So we get exactly this counterpart to the smooth setting which I have explained before. So these normals are interesting in architecture, for example, for the beam layout, because if you have such prismatic beams, yeah, you can align them so that their central planes are in these gray planes, and then you will have what is called a node axis where these planes meet in a precise way. And one will not appreciate this if you see just these figures, but if you look at the big mesh which will happen for a triangle mesh where 6 beams generically will meet, and where you will never be able to achieve such a node axis unless all node axes are passing through a given point, which would more or less mean that your surface is close to a sphere or a plane. So this having such nodes around is special, and here is just an example of such a conical mesh. So we have faces are as rectangular as possible. You have a natural support structure and a few other properties which I do not want to mention. Just as a side remark, this is an example where the architectural application actually led to something in mathematics. So later, when we studied this in more detail, we found actually a new curvature theory for polyhedral surfaces, and I do not want to explain this in detail. Just mention it can be that the application also feeds back to the mathematics. And by the way, this theory applies to everything except the triangle meshes, because the theory is built on the concept of parallel meshes, and we call two meshes parallel if they have the same combinatorics. So you have a one-to-one relation between vertices, edges, faces, and so on, and of course the valence is the same. So for example, this edge is parallel to this edge, and so on. Corresponding faces are parallel. But if you have a triangle mesh, the parallel meshes are trivial, because if you have two triangles with parallel sides, they are similar to each other, which implies that parallel triangle meshes would be scaled versions of each other, and then you cannot do anything good with that. Now, we can also model now with developable surfaces, and they also came up in architecture. So Frank Gehry's designs are famous examples of architectural designs which are largely based on developable surfaces, already indicated in the way how he builds it, how he clads it. If you clad with metal panels, and of course it is the easiest to have them developable, because you do not need any complicated forming process. And how will we achieve it? We take a planar, well, how can we achieve developable panels or developable strips? Again, very closely related to this planar quad stuff. Think of a planar quad mesh, and think of refining it in one direction and keeping it in the other direction. So we will refine in one direction, then we will get here these developable strips as outlined before. So we will get a representation at the end where a surface is composed of strips of developable surfaces. In this direction the stuff is smooth, but in the other, of course, we have still these polylines. And again, this feeds back to the theory, because the theory of semi-discrete representations is not exactly the smooth theory, and it is not exactly the fully discrete theory. It is in between, and there are a few questions which you need to treat separately. And actually an application is this Eiffel Tower pavilions, which originally was this developable strip model, but later for fabrication, the strips here have been approximated by right circular cylinders, because in this case the glass can be bent more easily. This is just motivated by production. Then I would like to briefly address something I have done with Niloy Mitra some years back in 2011. We would like to explore the space of constrained meshes, and in this case here polyhedral meshes. So we have an input mesh with a set of nonlinear constraints, for example, planarity of faces, and the goal is to explore neighboring meshes. So I give you an example. This is the input mesh, and here we have various design variants that also satisfy the constraints and have some kind of similarity to the original model. And I would like to outline the idea. The idea is to go into a high-dimensional space where a mesh in 3D in this high-dimensional space is just a single point. And the concept is super trivial. This is not something very abstract mathematically. I mean, a mesh has a certain number of vertices, say here n vertices. These are 3n coordinates, and these are the 3n coordinates of this point. I do not claim that this is the most clever way of getting these high-dimensional models. There are for sure more clever ways, but this is one way in which it works. And then we have various constraints. Each constraint is a certain equation on the mesh vertices. And in this high-dimensional space, one would call a constraint will be represented as a hypersurface. And you have to intersect all of these, which will give some I call it here a manifold. In mathematical terms, it is not quite true, but let's say it is a manifold. And we would like to extract and explore the desirable parts of this manifold, because just respecting the constraints is not enough. You have seen before there are meshes which have perfectly flat faces, but they may not have nice mesh polylines like here. So this is not a nice mesh. This is more or less useless, but this is a nice one. So we also have to filter out the useful one. So what we did with Nilo, and it took us surprisingly long time, and one reason is that we wanted to approximate this manifold not only to first order, so tangent space, super easy. We also wanted to look at curvatures, but as a differential geometer, you know, the curvature theory for manifolds in high dimension, which are not of codimension 1. So if in an n-dimensional space your manifold has dimension n-1, the curvature theory is as simple as in 3D for the surfaces. But if it is this difference, yeah, to the dimension of the embedding space gets higher, then it gets more complicated. The theory gets more complicated. So eventually we could avoid to really go into a big curvature theory. We could find some nice local approximation in a certain way, which I do not explain, and which allowed us to explore the neighborhood a bit further than just using a tangent space. And the good meshes we could characterize by certain functions, energies maybe, and a low value of that energy would characterize a good mesh, and a high value would characterize a bad mesh. And then you can do, say, spectral analysis on these functions, and then you find out the good subspaces in which you can explore. And for example, here is a 2D slice, yeah, through the tangent space, which gives you a certain two-dimensional part locally of this constraint manifold which you can explore. And instead of talking too much, maybe I show a video. So the idea here is the following. We give a flat mesh. The perfectly flat mesh also must sit in this manifold, right? Of meshes which are having flat faces. But here we require more. We require a circumcircle for each face, so a circular mesh. We start with a flat circular mesh, and then we try by shape exploration, we call this shape exploration, to get a 3D version of it. Yeah? And I hope that this video works. Yes, in fact, it works. So this is a flat mesh. You see, it's really a flat mesh. This is the panel, one of these good subspaces, and the user can go around here. As long as you are inside this boundary, you will meet the tolerances which you would like to have. And of course, there would be many other slices that you also can explore, but you would find somehow some natural ways for the given combinatorics designs which fulfill this. So far, I have only talked about aspects of manufacturing. So I talked about flat panels, which is, of course, nice. Yeah? This is always easy to manufacture. I talked about developable panels, which is, depending on the material, it can be good or not. So a general developable panel for glass is terrible, but for metal, it is good. Yeah? But I did not talk about another important aspect, namely about statics. After all, this stuff should stand, and it could be hard for the engineers to make it stand, and it could be easy. So maybe one wants to incorporate this. And this leads to work with guys named here, especially mention Etienne Wuga, who at that time was visiting us in Saudi Arabia from Columbia University in the US. And we worked on the design of self-supporting surfaces, and we have been motivated by a group of researchers, most notably Philip Bloch, who wanted to do masonry in freeform shapes, and we would like to have a simple design tool that generates such freeform structures. So they should be self-supporting. It's clear what this means. But we have been interested also whether there is a relation to discrete differential geometry, and whether we can make our planar quad meshes, these support structures, also self-supporting. So self-supporting planar quad meshes. A little bit on the methodology. Such a, let's say, masonry structure. is self-supporting if you can find inside this structure a so-called thrust network. A thrust network is a network of compressive forces inside the envelope which balances the load, so compressive forces. So in mathematics terms, these are the edge vectors coming in at a certain node. At this node, of course, you have to lump together locally the mass of the structure, the weight of the structure. Then you have these force densities here, which have to be positive, compressive, yeah? And this should balance the loads. You see already the first two coordinates of this vector are 0, which means vertical loads only, so the C coordinate is horizontal, balances the loads. If I omit the third coordinate here, or in other words, I project this thrust network into a plane, I have a planar system of forces which is in equilibrium, and as such, it is a discrete version of a planar elastostatic state. And in mechanics, people know such a planar elastostatic state has a so-called airy stress potential. And this airy stress potential here is a very nice discrete version. This is a surface, yeah, C equals f of xy, the airy stress potential. And here it is just a convex polyhedral surface vertically aligned with this horizontal force system. Vertically aligned means so the top view of this is exactly your force system. And even more interesting, actually, the angles here along the faces, so these are flat faces, and the angles are related to the forces. It is not the Euclidean angle, it is a non-Euclidean angle, and I don't want to go into detail, but it's easy to compute. This is not some very high geometry, it's easy to compute. So, and now the airy stress surface can be used to do something which appears very strange, of course, at first sight. We charge the curvature behavior of our self-supporting surface with respect to the airy stress surface. In three-dimensional classical differential geometry, you could say that you charge the curvature of a surface relative to a sphere. And if you look at differential geometry, in fact, you map the surface to the sphere with help of parallel tangent planes, and this gives you this Weingarten map if you differentiate, and so on. And this is very similar. I do not go into detail because it would lead too far, and I just want to have one theorem here. Yeah? Mathematician always has to have a theorem around, and please don't read it. Just I want to say that this equilibrium, force equilibrium, you can express in terms of curvatures. This relative mean curvature of the self-supporting surface with respect to the airy stress surface times some curvature of the airy stress surface, which I do not explain in detail, equals these loads, the forces. And this, at first sight, is totally useless, but in a few minutes I will show you something where it is actually very important. So what we also wanted to, of course, is to do some modeling. So can we do the following? This is a surface which obviously is not self-supporting because it has this part and it will always fall down. Yeah? It cannot be supported. Can we minimally change it? Of course, we would have to lift it up so that the structure is self-supporting. And it turns out this is actually a relatively simple optimization problem. We have to make sure that our mesh becomes a thrust network. And then you can do even things like this. I don't show it because it is a beautiful design. It is a terrible design. Look. But it is interesting because it has so many holes. And an object which has so many holes is very unlikely to be self-supporting. So this was somehow interesting to us. And I want to show here a video, but I'm not sure whether I'm finding this so easily. Yeah, here it is. So you start with some initial shape, in this case already motivated by some theory, but this is not so important. And this is a modeling system where you basically press a certain button and then it makes your stuff self-supporting. And during this editing session, where you see a little bit now of such an editing session, what you see here is just take a few points and change them. This is standard mesh editing, mesh deformation. And of course, if you deform a mesh into another shape, the shape will no longer be self-supporting, but there will be a closest shape that is self-supporting. And the question is, can we get it quickly? And you see we can get it rather quickly. yeah, what is next? I think the whole bottom is moved down a bit simultaneously, and you see already during doing it how the shape changes, and again attains such a self-supporting shape. What you see here, this black mesh, is a thrust network, and you see it's getting dangerous because it's too coarse. So you want to subdivide now, and of course then the shape should not change so much if you apply this green button, and really this happens. But then you have a better resolution, and then you can change the boundary conditions here, so no longer clamp it to the ground, and you can move it up and still make sure that it is self-supporting, so the surface has to lean back a little more. Maybe what I really like is if you cut here out a whole row of this model. You tell me, but we still have time. Oh yeah, it's easy. And you see, while cutting, already the shape changes here, and it has to open a lot more in order to stay self-supporting. You can do things which you can do in other systems as well, as maybe grabbing a point and moving it up and so on. So maybe we have already seen enough of that. I just wanted to show you, this is what I call fabrication, and in this case statics aware design. Is not just designing a geometry, having a lightweight judgment of whether this is feasible. I do not claim that it would replace a thorough treatment by an engineer using finite elements. Of course you have to do it, but the probability that you do not have to change much if you have done this simplified model is very high. And we ran experiments actually, then you feed it into ANSYS and you check whether this is really working out, and it turns out that it is. So where is my aha here? Yeah, another problem. If we have a self-supporting shape, can we represent it by a planar quad mesh? So that basically this planar quad mesh is the thrust network. Yeah? Well, this turns out to be non-trivial, and it is related to this curvature theory I have mentioned before. It turns out that such a PQ mesh, which is self-supporting, is a discrete version of the network of relative principal curvature lines. Before we had the Euclidean principal curvature lines. Now I said, oh, we can replace actually the Euclidean sphere by this stress surface. And you can also do things like principal curvature lines you can transfer. And if you lay it out according to that, your optimization will work. You get such steel glass structures with low moments in the nodes. But the pure optimization will fail. So if this is a self-supporting structure, you prescribe the combinatorics of your quad mesh. You try to optimize so that you keep the force balance and you keep the planarity of faces, and this is the best you can do. But if you lay out your mesh according to what I've said before, the best you can do is this. And this is relatively similar to that. It's a little bit distorted from this angle, but of course much better than that. And now I want to show you something very new and unpublished. I talk here about form finding with polyhedral meshes and about a fast way of projecting onto such a constraint manifold. So let me first come from the application side. Let us assume we are given a boundary and we would like to put a mesh inside that boundary which is well aligned with the boundary, for example, has planar faces, for example, also is in static equilibrium, maybe even with compressive forces. So subject to a variety of constraints. Well, why is this not so easy? We could, of course, do what I have just said. Having a boundary, we use standard form finding and get the form, and then remesh, say with a planar quad mesh, but then we will get something that is not aligned well with the boundary. So there we have a problem with the boundary. And then we could have also another approach. If we have a flat boundary, we would say, oh, this is very easy. We just choose some combinatorics of a mesh that obeys this boundary. You're just in the plane, and then use this magic tool, which I have shown before, namely this shape space exploration, and let's move out in the shape space. But unfortunately, it turns out that in general, the shape space is not so nice to us, because the mesh we are going to start with most likely lies in a, let's say, trivial component of that shape spaces. So this is the shape space of all meshes of a given combinatorics which have planar faces. And of course, a trivial thing is if all vertices lie in a fixed plane, the totally flat ones. And the totally flat ones actually in this shape space express themselves in also a linear space. But the interesting part here of the shape space you will not reach directly, because your initial mesh will be in the trivial part. The thing which I showed you before with this exploration from the circular mesh, the circularity made sure that this extraneous part disappears. You can prove it. But in general, it is around. So actually, one would need something that moves you here. And by the way, it's interesting, is related to forces. If you have a mesh which is not, where you have no forces, that brings it into equilibrium, you are here. But if you can find forces, you have to change the mesh a bit, so that the mesh is in equilibrium. You are already here, and then the shape exploration would work. But we wanted to do something maybe slightly more direct, namely, given a mesh, modified so that it fulfills the constraint and is suitable for the application. Mathematically speaking, we have this constraint manifold or shape space, whatever you call it. We have a point that is outside this shape space because the mesh doesn't fulfill the constraints yet. And we would like to project onto this shape space, but onto the good part. The output should be a nice mesh and not a bad one, obviously. And there are two key ingredients to achieve this. Well, this is the first one. We introduce more variables. So at first sight, this looks like a totally crazy idea. You make the problem even more complicated by getting more variables. But we introduce them so that the constraints are at most quadratic. So let me give you an example. If we have to express the planarity of a face, we would introduce as an additional variable the normal vector of the face. So this is three scalar variables, of course. And then we would express orthogonality between the normal vector and the edges of that face. This sounds very nice, but we could run into trouble, because for an n-gon, if we assure only n-1 of the edges to be orthogonal to this normal, the nth edge automatically will be orthogonal to that normal, obviously. This means that if we take all n edges and express their orthogonality, we have dependent constraints, which will make a lot of trouble in numerical optimization, most notably in those which use Lagrangian multipliers and so on. So in all these theorems in numerical optimization, you see, assuming that the constraints are independent and then this holds. But in the approach which we use, is not the problem, because we really want to use all n edges. Otherwise, yeah, it is a combinatorial nightmare to select those ones which you really use. And the second key ingredient, do not use constraint optimization. So what do we use instead? We just linearize the constraints, and somehow, obviously, this quadratic nature of the constraints makes sure that the linearization is not that bad. In fact, one understands pretty well what happens if you have a quadratic constraint, what the linearization does. For higher order, this is not so clear. And then we just add the conditions for an unconstrained minimizer of an appropriate energy, say fairness, and so on. So these are all linear equations, because we make sure that the energy is quadratic. And then, yeah, I forgot, when we linearize the constraints, we are still having a nightmare, because we will have a badly behaved, underdetermined system. Yeah, like if you have in 3D three planes which pass through a straight line, ideally due to numerical errors, they will not pass exactly through a straight line, but the intersection can be anywhere, even at infinity. So it could be really bad. So and then we add these conditions, and then we just solve this overdetermined linear system in a least square sense, which is stable, and we put much higher weights to the constraint equations, and we use these conditions for an unconstrained minimizer as a kind of regularizer. So when I view it as a Newton method for the solution of a system of nonlinear equations, an underdetermined system, which is guided by, regularized by a low value of an appropriate energy, so we call it a guided projection onto the constraint manifolds. And here's the experiment. So we compare two of the leading methods, most recent ones from Mark Pauli's group at EPFL, so augmented Lagrangian with all kinds of specialties, with a method where we ignore the quadratic constraint, we use cubic constraints and everything else, and our final method. And you would see the first three with respect to the decay of the error are here, and the fourth method goes quickly down, and then, of course, there is not so much progress anymore. And this gives opportunity, of course, to get real-time modeling, and you can have many types of constraints, like the structural constraints, also inequalities. An inequality, so that something is greater or equal 0, we just introduce an additional variable, dummy variable, and we say the constraint, this equals the square of this dummy variable. So it has to be positive, right? It's a square of a real number. And it is quadratic, so it fits into this fits into the system. So this is important. And of course, negative you can also. I show you some results. So this is a structure which is made from planar quadrilaterals. It is actually self-supporting. So this is an example of a structure which is not a height field. Yeah, it has overhangs, obviously. Yeah, there's overhanging parts. It is still self-supporting. The alignment with the ground is good. Maybe this rendering hides a little bit. So the actual ground is along exact face diagonals here. So this is a good boundary alignment. So here's another view. You can do various things. We have a mesh with planar quads, and we increase the volume. Or what I like, we can do force fairing. So in engineering, maybe you like a good distribution of forces. So here, this is the initial solution, force equilibrium, but you see very different forces here by the color coding. And then you optimize or you change it so that opposite edges have nearly, in each face, have nearly the same force. And interestingly, not only, of course, you get the better distribution of forces, it also has a geometric effect. So that it looks a bit nicer, a bit fairer in even. Then, boundary given, we can try different combinatorics. The good news is the useful stuff may not have so much different in shapes. And this is not necessarily bad news, because one aspect of the design is combinatorics, yeah, and if several combinatorics can lead to roughly the same design, not precisely, this is useful. Yeah, a few examples. So the basic case, extend a shape over a rectangle, so some inner chord, for example, you can solve. Of course, it's also in force equilibrium, or a more complicated one. And as last, I show you a video. Nilo, am I still allowed to show the video? Well, I have to get his agreement first. Yeah? Just to show you that this is modeling in real time. So the first thing is just, we have a flat mesh, and interactively you lift up, and you see when it gets blue, it is flat. And this is really very fast. So this is not optimization anymore. This is this guided projection. And those who have worked in this field and know that it's not so easy to planarize these things, will appreciate more. Others will say, well, this is just some typical computer graphics where you can quickly do various fancy things. So it is doing surprisingly well, even also to us. Yeah? And it quickly adapts actually to what you like. And this is a design made from this example. And then we do it for a non-flat boundary. And these faces are at first very non-planar. And during this modeling, you see it immediately adapts to blue, and blue means flat faces. So here we did not yet look at force equilibrium, so let us look at, this next is circular meshes, I'm sorry. these a little bit tougher constraints, these circular meshes, so you cannot get such a huge variety in the neighborhood of your design, but you still see it is pretty interactive. And of course, it is a discretization of a principal curvature line parameterization. So this is a more restricted scenario. Then we look at static equilibrium. Here we allow tensile and compressive forces. This shows such a modeling session where we basically have a subdivision modeling and this quick projection onto this constraint manifold to make the faces planar and to achieve static equilibrium. So here you again design an overhang, which is not so surprising because you allow tensile forces. Yeah? And of course, if you move it forward, because of the tension forces, it is able to lean forward here. But we may add a restriction that the forces are only compressive, so self-supporting. And we do a similar example, and we can also try to model an overhang, and here is this overhang. And then you could also try whether this shape is able to lean forward, and hopefully it is not. Yeah? Otherwise it would really look bad, and you see, no, it doesn't want to lean forward. It will go down a bit. Yeah, that's exactly what you want to see here. And I will not show more than just the final transparency. So as a conclusion, I hope that I could show that this differential geometry is a bit useful and that the combination with numerical constraint solving, this is what we did actually at the very end, and optimization, this helps in designing and finding and developing computational design tools which combine shape modeling with aspects of function and fabrication. And of course, what I have shown here, this is architecture, but the mathematics is applicable to more general scenarios. So this constraint solving, this guided projection, we are pretty sure it is going beyond architecture. And here is one guy, Niloy Mitra, who has looked at areas that go beyond architecture. I think that this geometric modeling, but this is well known, this geometric modeling part of the product life cycle is a main productivity bottleneck. So a lot of money can get lost here, so it would have a huge economic impact, actually, if one achieves more here. The problem is they're at various places, including my own one or Niloy's or others. People do a little bit here, a little bit there. Also somehow, maybe sometimes a bit isolated. And I think it would require a more interdisciplinary effort to embed this current scattered work into a much more systematic program on, one may call it smart modeling tool or however. And I hope that we will, at least the two of us, yeah, end up with a better cooperation. And because here in London we would have great access to all these fancy architecture firms, and so there's lots of possibilities, and of course it goes way beyond architecture, and also here in London this is a good place. So with this, I hope that I didn't bore you too much with mathematics, and I'm happy to answer questions, maybe now or later if we have some other way of discussing this. Thank you very much for your attention.